We just solved faster-than-light travel. Well, not exactly. A team of physicists did in May 2024. They published a warp drive design that doesn't violate the laws of physics. Yes, you heard that correctly. A real, mathematically sound warp drive, the kind that could take you to another star system within a human lifetime. This isn't science fiction anymore, and we need to talk about it immediately. Let's begin. Here's the reality we face. The universe is breathtakingly, almost cruelly, vast. Light, the fastest thing we know, takes over 4 years to reach Proxima Centauri, our nearest stellar neighbor. With our current rocket technology, that same journey would consume tens of thousands of years. Multiple human lifetimes would pass before a spacecraft could even send back a single photograph. The Voyager 1 probe, humanity's most distant ambassador, launched in 1977, has barely scratched the edge of our solar system. At its current velocity, it would need 70,000 years to reach another star, if it were even heading toward one, which it isn't. This isn't just inconvenient. This is a fundamental barrier between us and the cosmos. It means that the beautiful exoplanets we discover orbiting distant suns, the potentially habitable worlds that might harbor life, remain forever out of reach using conventional propulsion. Chemical rockets, ion drives, even theoretical nuclear fusion engines can't overcome the tyranny of distance. The speed of light, roughly 186,000 miles per second, or about 300 million meters per second, represents an absolute cosmic speed limit according to Einstein's special relativity. As you accelerate, your mass effectively increases, requiring ever more energy to push faster. To reach light speed would demand infinite energy, something the universe simply doesn't provide. Scientists have long understood this cosmic catch-22. If nothing can exceed light speed, then interstellar exploration becomes a multi-generational endeavor at best, or an impossible fantasy at worst. Yet the universe itself offers a loophole, one that Albert Einstein himself discovered when he revolutionized our understanding of gravity in 1915. His general theory of relativity revealed that space and time aren't fixed backdrops where events unfold. Instead, they're dynamic, flexible, woven together into what we call space-time. Massive objects like stars and planets warp this fabric, creating the phenomenon we perceive as gravity. But here's where it gets interesting. If massive objects can bend space-time, what if we could manipulate that bending ourselves? What if we could create a bubble where space-time contracts in front of a spacecraft and expands behind it, carrying the vessel forward without the ship itself ever accelerating past light speed locally? The ship wouldn't move through space in the traditional sense. Space itself would move around the ship. This is the core concept behind what physicists call a warp drive. The idea first entered serious scientific discourse in 1994, when Mexican physicist Miguel Alcubierre published a groundbreaking paper. His mathematical solution to Einstein's field equations described exactly this scenario: a spacecraft surrounded by a warp bubble, surfing on a wave of distorted space-time. Inside the bubble, space-time remains flat and normal. Passengers would feel no acceleration, no crushing g-forces. Outside, space-time performs an elegant cosmic dance, contracting ahead and expanding behind, propelling the bubble forward at velocities that could, in principle, exceed light speed from an outside observer's perspective. Think about it this way. Imagine you're standing on a moving walkway at an airport. You're walking at your normal pace, say 3 miles per hour, but the walkway itself moves at another 3 miles per hour. Relative to the terminal, you're traveling at 6 miles per hour, even though you're only exerting enough effort to walk at 3. The Alcubierre drive works on a similar principle, except instead of a walkway, you're manipulating the cosmic infrastructure itself. The spacecraft doesn't violate relativity because within its local bubble of space-time, it isn't moving faster than light. It's space-time doing the heavy lifting. This sounds incredible, and for 30 years, it remained firmly in the realm of theoretical speculation. Why? Because Alcubierre's original design had a devastating requirement. It needed something called exotic matter, specifically matter with negative mass or negative energy density. To understand how bizarre this is, consider that every particle, every atom, every object you've ever encountered has positive mass. Negative mass would behave in ways that defy intuition. Push it, and it would accelerate toward you instead of away. It would fall upward instead of downward in a gravitational field. The problem is, we've never observed negative mass in nature, not once. Quantum field theory suggests that tiny, fleeting violations of positive energy might occur at subatomic scales for infinitesimally brief moments, a phenomenon related to vacuum fluctuations and the Casimir effect. But harnessing these quantum quirks to generate the enormous quantities of exotic matter needed for a macroscopic warp bubble, that seemed not just technologically impossible but potentially forbidden by the fundamental laws governing our reality. If you're finding this fascinating and want to explore more cosmic mysteries, consider subscribing and hitting that thumbs up button. It truly helps this channel grow and allows me to bring you more content about the cutting edge of space science. Your engagement makes all the difference. For 3 decades after Alcubierre's initial paper, physicists treated warp drives as interesting mathematical curiosities, useful for exploring the boundaries of general relativity, but not realistic engineering projects. Some researchers worked to reduce the exotic matter requirements, tweaking the geometry of the warp bubble to minimize how much negative energy you'd theoretically need. Others explored whether quantum effects might provide loopholes. But the fundamental barrier remained: you couldn't build a warp drive with normal matter, the protons, neutrons, electrons, and photons that constitute everything we know. Then came May 2024. A team led by Dr. Jared Fuchs at the University of Alabama in Huntsville, working with the Advanced Propulsion Laboratory at Applied Physics, published research that represents a genuine paradigm shift. Their paper, titled Constant Velocity Physical Warp Drive Solution, appeared in Classical and Quantum Gravity, one of the most respected peer-reviewed journals in gravitational physics, and it presented something nobody had achieved before: a mathematically rigorous warp drive model that uses only positive energy, no exotic matter, no violations of known physics. Let that sink in for a moment. For the first time in the history of warp drive research, scientists demonstrated that you could create a bubble of warped space-time capable of transporting objects without requiring substances that might not even exist. This doesn't mean we're building warp ships next year. The engineering challenges remain staggering, the energy requirements immense. But it means the concept has crossed a critical threshold from probably impossible to extraordinarily difficult, but perhaps achievable with advanced technology. The research team includes Dr. Christopher Helmerich, also from UAH, along with Dr. Alexei Bobrik, Luke Sellers, Brandon Melcher, and Gianni Martia from Applied Physics. Together they constructed what they call a constant velocity physical warp drive solution. The term constant velocity is significant. Their design maintains a steady warp speed, avoiding the complications that arise during acceleration and deceleration, where energy requirements typically spike catastrophically in earlier warp models. By focusing on constant motion, they simplified the mathematics and reduced the exotic energy demands. Here's how they did it. The team modified the geometry of the warp bubble itself, the specific shape of how space-time curves around the spacecraft. Previous designs, including Alcubierre's, created steep, abrupt gradients in space-time curvature, sharp transitions between the compressed space ahead and the expanded space behind. These sharp transitions were what demanded exotic matter. The new design uses a more gradual, shell-like structure with carefully calibrated layers of positive energy density. Think of it like this. Imagine trying to move a heavy object. If you push it with a single sharp point, you need enormous pressure concentrated at that point. But if you distribute the force across a larger surface with a gentler slope, you can achieve the same movement with far less stress on any single point. The Fuchs team applied similar reasoning to space-time geometry. By spreading out the curvature more smoothly and using a specific mathematical configuration called a shell solution, they eliminated the need for negative energy entirely. The technical details involve sophisticated tensor calculus and Einstein's field equations, mathematical tools that describe how matter and energy curve space-time. But the breakthrough boils down to this. By engineering the right distribution of positive energy in the right geometric configuration, you can create a warp effect that moves a region of space without violating energy conditions. Energy conditions are fundamental principles in physics that describe how matter and energy must behave. The null energy condition, for instance, states that energy density measured by any observer moving at light speed cannot be negative. Previous warp drive models violated these conditions. The new design respects them. Now, before we go further, there's something crucial to understand about why this matters so profoundly. It connects to the fundamental nature of space, time, and motion. When objects approach light speed through normal acceleration, time itself begins to behave strangely. This phenomenon, called time dilation, is one of the most experimentally verified predictions of Einstein's relativity. Clocks moving near light speed tick slower relative to stationary observers. Astronauts traveling at extreme velocities would age more slowly than people back on Earth. This creates a peculiar paradox for interstellar travel. Even if we somehow built a spacecraft capable of reaching 99% of light speed using conventional propulsion, the journey to a star 10 light-years away would take just over 10 years from Earth's perspective. But for the astronauts on board, due to time dilation, the journey might feel much shorter, perhaps only a year or two of subjective time. They would return to find decades had passed on Earth, their loved ones aged or gone. If you want to dive deeper into this mind-bending consequence of relativity, I've created another video exploring exactly why time slows down at light speed, examining the experimental evidence and what it means for our understanding of reality. The link is in the description and pinned on the comments. It's fascinating stuff that complements what we're discussing here. But here's where warp drives offer something radically different. They sidestep time dilation entirely. Because the spacecraft inside the warp bubble isn't actually moving through space at relativistic speeds locally, time inside the bubble flows normally. You don't experience the time distortion that comes with high-velocity travel. You could journey to a distant star and return to Earth having aged the same amount as everyone back home. This is one of the most appealing aspects of warp technology. It defeats not just the distance barrier, but also the temporal consequences that make conventional, near-light-speed travel so problematic for maintaining connections across space. The Fuchs team's design specifically addresses constant velocity scenarios, meaning once you've established your warp bubble and set it in motion, you cruise at a steady rate. This avoids the enormous energy spikes associated with accelerating the bubble itself. In earlier models, just getting the warp bubble up to speed required absurd amounts of energy, sometimes calculated to exceed the mass energy of entire planets, converted into pure usable power. By stabilizing at constant velocity, the new model makes the energy requirements more manageable, though still astronomical by current technological standards. Let's talk numbers. Keeping in mind these are theoretical calculations based on the model's mathematics. The energy needed depends on the size of the warp bubble and how fast you want to go. For a bubble large enough to contain a spacecraft, even traveling below light speed, you'd need energy equivalent to large masses. We're not talking about rocket fuel here. We're talking about harnessing energy on scales comparable to small planetary masses or the total power output of stars over extended periods. This isn't something we can do today, tomorrow, or likely within this century. However, and this is critical, the energy required is no longer infinite or impossible in principle. It's finite, calculable, and uses only positive energy, the kind that actually exists in our universe. That transforms warp drives from science fiction into engineering challenges. Extraordinarily difficult engineering challenges, to be sure, but challenges nonetheless. And history teaches us that humanity has overcome seemingly impossible engineering barriers before. Powered flight seemed absurd until the Wright brothers succeeded in 1903. Spaceflight was fantasy until Sputnik launched in 1957. Nuclear fusion for energy production remains elusive, but appears increasingly achievable. The warp drive model uses what physicists call stress energy distributions. Essentially, you need to arrange matter and energy in precise configurations to generate the desired space-time curvature. One approach might involve ultra-dense materials, matter, compressed to extraordinary densities, but still maintaining positive mass. Another could leverage electromagnetic fields of immense strength, since electromagnetic energy also contributes to space-time curvature. Powerful lasers, particle beams, or even hypothetical materials like stable strange matter might play roles in future designs. Strange matter, for context, is a theoretical form of matter composed of strange quarks in addition to the up and down quarks that make up normal protons and neutrons. Under certain extreme conditions, like those inside neutron stars, strange matter might be stable and possess exotic properties that could aid in manipulating space-time. We haven't confirmed strange matter's existence definitively, but it doesn't violate known physics the way negative mass does. It's speculative, but possible. Another fascinating aspect of the new warp drive design involves the bubble's geometry. The research describes a shell-like structure with multiple layers, each contributing to the overall space-time distortion. Imagine concentric spheres of carefully tuned energy density working together like the layers of an onion. The innermost region, where the spacecraft sits, remains flat and undistorted. The outer shells gradually bend space-time, creating the warp effect that propels everything forward. This layered approach distributes the gravitational stress more evenly, preventing the extreme curvatures that would require exotic matter. The mathematics behind this involves solving Einstein's field equations with specific boundary conditions. These equations relate the curvature of space-time to the distribution of mass and energy. They're notoriously complex, a set of 10 interrelated differential equations that describe how every point in space-time responds to matter and energy around it. Finding solutions that represent physically realizable scenarios, especially exotic ones like warp bubbles, requires sophisticated computational tools and deep theoretical insight. The Fuchs team employed numerical methods and analytical techniques to explore the solution space, searching for configurations that satisfied all the necessary physical constraints. One constraint they had to respect is called the weak energy condition, which essentially states that energy density cannot be negative for any observer. Another is the dominant energy condition, which ensures that energy doesn't flow faster than light. These conditions aren't arbitrary rules. They emerge from our understanding of thermodynamics, quantum field theory, and observational astronomy. No object we've ever measured violates them. Previous warp drive models, by requiring negative energy, necessarily violated these conditions, placing them in a category physicists call exotic solutions, interesting mathematically, but not physically realizable with known matter. By constructing their solution entirely from positive energy configurations, the research team brought warp drives into the realm of classical solutions, ones that don't require new physics or undiscovered particles. This is analogous to the difference between proposing a machine that requires a perpetual motion device versus one that requires extremely efficient but thermodynamically allowed processes. The former is impossible. The latter is just really, really hard. Now, there's an important limitation to discuss openly because honest science means acknowledging what we don't know and what remains uncertain. The constant velocity warp drive design solves the steady-state problem beautifully, but real spacecraft need to accelerate, decelerate, turn, and maneuver. Starting the warp bubble, bringing it up to cruising speed, and then stopping it at your destination introduces additional complications. During these transition phases, the energy requirements might spike dramatically. The research team acknowledges this in their paper, noting that their solution represents a crucial step, but not the complete answer to practical warp travel. Additionally, there's the question of how you generate and maintain the energy distributions required for the warp bubble. It's not enough to calculate that you need a certain amount of energy in a certain configuration. You need actual physical mechanisms, devices, and systems that can produce, control, and sustain those conditions. This is where we move from theoretical physics into speculative engineering. Perhaps future advances in fusion power, antimatter containment, or zero-point energy manipulation could provide the necessary capabilities. Perhaps we'll discover entirely new energy sources or methods of manipulating space-time that we haven't yet imagined. Consider antimatter for a moment. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's famous equation E equals mc squared. This is the most efficient energy conversion process known to physics. Nuclear fusion, the process powering stars, converts less than 1% of mass into energy. Chemical rockets convert a tiny, almost negligible fraction. Antimatter offers theoretical efficiencies that could, in principle, provide the enormous energies needed for warp drives. The catch? Producing antimatter requires as much energy as you get back from annihilation, and storing it without letting it touch normal matter presents staggering technical challenges. CERN's Large Hadron Collider can produce antimatter atoms, but only a handful at a time, nowhere near the quantities needed for propulsion systems. Another energy source worth mentioning is the hypothetical zero-point energy of the vacuum. Quantum mechanics tells us that empty space isn't truly empty. Virtual particles constantly pop into and out of existence, creating a background energy field. The Casimir effect, experimentally verified, demonstrates that this quantum vacuum energy has measurable physical consequences. Two metal plates placed extremely close together in a vacuum experience an attractive force because certain wavelengths of virtual particles are excluded from the space between them, creating an energy imbalance. Some speculative proposals suggest tapping this vacuum energy, though extracting usable power from it remains deeply uncertain and potentially impossible without violating thermodynamic principles. What makes the 2024 warp drive research so significant is that it doesn't rely on these speculative energy sources. The model works with any positive energy, whether that's conventional matter, electromagnetic radiation, or hypothetical but physically allowed substances. This agnostic approach to energy sources means that as our technology advances, whatever breakthroughs we achieve in energy generation could potentially be applied to warp drive development. The physics doesn't depend on discovering something completely unknown. It depends on engineering something extraordinarily sophisticated from known ingredients. Let's put this in the broader context of humanity's journey into space. We're living through a remarkable era of astronomical discovery. The James Webb Space Telescope, which launched on December 25, 2021, has revolutionized our view of the early universe, detecting galaxies that formed just a few 100 million years after the Big Bang. These ancient light sources exist over 13 billion light-years away. their photons traveling across the expanding cosmos for nearly the entire age of the universe before reaching our instruments. Webb has also analyzed the atmospheres of exoplanets, distant worlds orbiting other stars, detecting molecules like water vapor, carbon dioxide, and methane. Some of these planets orbit within their star's habitable zone, the region where temperatures might allow liquid water to exist on a surface. The Kepler Space Telescope, which operated from 2009 to 2018, identified thousands of exoplanet candidates. We now know that planets are common, perhaps outnumbering stars in our galaxy. Many reside in potentially habitable environments. This creates a profound cosmic irony. We've discovered countless worlds we desperately want to explore, yet they remain impossibly distant. The TRAPPIST-1 system, discovered in 2017, contains 7 Earth-sized planets orbiting a small, cool star just 39 light-years away. 3 of those planets sit squarely in the habitable zone. With our current technology, reaching TRAPPIST-1 would require nearly 1 million years of travel time. Even with hypothetical fusion rockets that could reach a few % of light speed, the journey would still consume thousands of years, far beyond any human lifespan or even the expected duration of our current civilization. This is why warp drive research matters. It's not about satisfying curiosity alone, though that's valuable in itself. It's about transforming humanity from a single planet species confined to one fragile world into a truly interstellar civilization capable of exploring, understanding, and perhaps one day settling among the stars. The philosophical implications are staggering. Every human who has ever lived, every empire that has risen and fallen, every achievement and tragedy in our history, all of it has occurred on one tiny blue dot suspended in a sunbeam, as Carl Sagan so beautifully described Earth. Breaking free from that constraint would represent arguably the most significant transition in human history, more transformative than the agricultural revolution, the industrial revolution, or the information age. It would mean accessing resources, knowledge, and possibilities currently beyond our wildest imagination. It would also mean confronting profound questions about our place in the universe. Are we alone? If life exists elsewhere, what forms does it take? What can we learn from civilizations that might have millions of years of development beyond our own? The warp drive research also connects to fundamental questions in physics that go beyond propulsion technology. Understanding how to manipulate space-time curvature could shed light on the nature of gravity itself, one of the 4 fundamental forces. We have an excellent description of gravity through general relativity, but we still lack a complete quantum theory of gravity that unifies Einstein's geometric picture with the probabilistic framework of quantum mechanics. Experiments with controlled space-time distortion, even on small scales, could provide insights into quantum gravity, potentially resolving mysteries like what happens at the singularity inside black holes or what caused the Big Bang. Speaking of black holes, they represent natural examples of extreme space-time curvature. At the event horizon of a black hole, gravity becomes so intense that space-time curves back on itself, preventing anything, even light, from escaping. Inside, all paths through space-time lead inexorably toward the central singularity. The mathematics describing black holes and those describing warp drives share common features. Both involve solutions to Einstein's equations with unusual properties. By studying warp geometries, physicists gain tools and intuition applicable to understanding black holes, neutron stars, and other extreme astrophysical objects. Some researchers have explored whether warp drives might enable not just faster-than-light travel, but also time travel. In general relativity, certain space-time geometries permit what are called closed time-like curves, paths through space-time that loop back on themselves, theoretically allowing an object to arrive at an earlier time than it departed. These solutions fascinate physicists but also deeply trouble them because they create causality paradoxes. What happens if you travel back and prevent your own departure? Most physicists suspect that nature has some mechanism, perhaps related to quantum mechanics, that prevents these paradoxes from actually occurring, even if the mathematics of general relativity technically allows them. The Fuchs warp drive model operates at subluminal speeds, meaning slower than light relative to distant observers, which avoids the most severe causality concerns. However, if future refinements allowed superluminal warp speeds faster than light from an external reference frame, the possibility of time travel effects would need careful analysis. Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics somehow prevent time travel to the past, preserving causality. Evidence supporting this conjecture includes the fact that quantum effects tend to destabilize geometries that permit closed time-like curves, causing them to collapse before they can function. Let's return to the practical engineering challenges. Assuming you've solved the energy problem and can generate the massive amounts of power needed, you face the issue of controlling and shaping that energy precisely. The warp bubble requires specific energy distributions maintained with incredible accuracy. Any instability, any fluctuation in the field generating the bubble could have catastrophic consequences. At best, the warp effect might simply collapse, leaving you stranded in interstellar space. At worst, uncontrolled release of the energies involved could be devastating. Think about the precision required. GPS satellites orbiting Earth must account for both special and general relativistic effects to maintain accuracy. Time runs slightly faster for them because they're higher in Earth's gravitational field and slightly slower because they're moving relative to ground-based observers. The combined effect amounts to only microseconds per day, but without correcting for it, GPS coordinates would drift by kilometers. Now imagine the precision needed to maintain a warp bubble where you're deliberately manipulating space-time curvature on scales millions of times more extreme than Earth's natural gravity. The control systems would need to be extraordinarily sophisticated. Navigation presents another challenge. Inside your warp bubble, you're causally disconnected from the universe outside. Light from external sources can't normally reach you because of how space-time curves around the bubble. This means you can't observe where you're going or detect obstacles in your path. Interstellar space isn't completely empty. It contains gas, dust, stray hydrogen atoms, and occasionally larger debris. At warp speeds, even a collision with a single dust grain could release enormous energy. Imagine moving at significant fractions of light speed and hitting a pebble. The kinetic energy involved would rival nuclear weapons. Some proposed solutions involve sending probe beams ahead of the warp bubble or using gravitational sensing to detect mass concentrations in your path. Others suggest pre-mapping routes using conventional observations, essentially creating interstellar highways through well-surveyed regions of space. None of these solutions are simple and all require technologies we haven't yet developed. But again, these are engineering problems, not fundamental physics impossibilities. There's also the question of what happens to space itself as you travel. The warp drive compresses space ahead and expands it behind. What effect does this have on the ambient interstellar medium, the thin gas and dust between stars? Some calculations suggest that the intense gravitational fields at the bubble boundary might sweep up particles and radiation, creating a buildup of high-energy matter at the leading edge. When you decelerate and the bubble collapses, this accumulated energy might release in a catastrophic burst, potentially sterilizing anything in front of the spacecraft. This phenomenon, sometimes called the warp drive death ray, isn't confirmed, and different models yield different predictions, but it illustrates that warp travel might have side effects beyond simply moving from point A to point B. Understanding and mitigating these effects would be crucial before attempting any actual flight. You wouldn't want your arrival at a new star system to be accompanied by a gamma ray burst that destroys everything nearby. Despite these formidable challenges, the psychological and cultural impact of the 2024 research shouldn't be underestimated. For decades, scientists told the public that faster-than-light travel was impossible, full stop. Warp drives were fantasy, no different from magic wands or perpetual motion machines. This created a sense of cosmic resignation, a feeling that the universe's wonders would forever remain out of reach, visible only through telescopes, never through portholes. The new research changes that narrative. It says that while warp drives remain incredibly difficult, they're not forbidden by the laws of nature. They're conceivable, achievable in principle, worthy of serious study and incremental development. This matters for inspiring the next generation of physicists, engineers, and explorers. Young people today might reasonably dream of careers contributing to technologies that enable interstellar travel. That dream, previously dismissed as unrealistic, now has legitimate scientific foundation. Universities and research institutions have taken notice. The Advanced Propulsion Laboratory at Applied Physics, where several of the research team members work, focuses explicitly on breakthrough propulsion concepts. NASA's innovative Advanced Concepts program has funded preliminary studies of warp drives and related exotic propulsion ideas. These aren't massive investments, but they represent a shift from complete dismissal to cautious exploration. Private companies have also shown interest. While no one is currently building a warp drive, corporations investing in long-term space infrastructure recognize that revolutionary propulsion technology could transform economics and exploration. Companies like SpaceX and Blue Origin focus on making space access cheaper and more routine using conventional rockets. But some visionaries look further ahead, funding research into concepts like fusion propulsion, antimatter engines, and yes, potentially warp drives. The timeline for practical warp technology remains deeply uncertain. Optimists might suggest centuries, pessimists would say never, arguing that engineering challenges will prove insurmountable even if the physics technically allows it. A reasonable middle estimate might place functional warp drives, if they're achievable at all, somewhere in the range of multiple centuries to a millennium from now. That seems impossibly distant, but consider that the gap between the Wright brothers' first flight and landing humans on the moon was only 66 years. Technology can advance faster than we anticipate when sufficient resources and motivation align. There's another dimension to this story worth exploring: the international nature of breakthrough science. The research team that developed the new warp drive model spans institutions and represents collaborative effort across borders. Dr. Alexei Bobrik, one of the co-authors, has worked extensively on advanced propulsion concepts and contributed to multiple papers exploring the boundaries of general relativity. This kind of international collaboration characterizes modern physics. The problems we face are too complex, too fundamental for any single nation or institution to solve alone. Consider the history of relativity itself. Einstein developed his theories while working as a patent clerk in Switzerland, building on electromagnetic research by Maxwell in Scotland, Lorentz in the Netherlands, and Poincaré in France. When his ideas needed experimental confirmation, British astronomer Arthur Eddington led expeditions to observe the solar eclipse of 1919, measuring how the sun's gravity bent starlight exactly as Einstein predicted. Science transcends borders because physical laws remain constant everywhere. An equation that describes space-time curvature works the same whether you're in Alabama, Moscow, or Beijing. This collaborative spirit will be essential for warp drive development. The resources required, both intellectual and material, will demand global cooperation. Just as the International Space Station represents partnership among 15 nations, and the Large Hadron Collider involves thousands of scientists from over 100 countries, any serious effort to build warp technology would necessarily be a species-level project, not a national one. Let's think about the scientific method itself for a moment. What makes the warp drive research legitimate science rather than speculation? It comes down to testability and mathematical rigor. The researchers didn't just imagine a warp drive and declare it possible. They constructed a specific mathematical model, solved Einstein's field equations explicitly for that model, demonstrated that the solution satisfies known physical constraints, and published their work in a peer-reviewed journal where other experts could examine and critique it. Peer review is crucial. Before classical and quantum gravity published the paper, independent physicists reviewed the mathematics, checked the derivations, and verified that the conclusions followed from the premises. This process isn't perfect, errors occasionally slip through, but it represents our best method for maintaining scientific standards. The fact that the warp drive paper passed this scrutiny means the physics community has validated that yes, within the framework of general relativity, this design works mathematically. However, mathematical consistency doesn't guarantee physical realizability. Physics history contains examples of mathematically valid solutions that don't correspond to anything we can actually build. The Schwarzschild solution, which describes black holes, is mathematically sound, but we can't create a black hole in a laboratory because concentrating that much mass in such a small space exceeds any technology we possess. The question for warp drives is whether they fall into the category of valid but impractical, or valid and potentially achievable with sufficient advancement. The 2024 research moves warp drives closer to the latter category by eliminating the exotic matter requirement, but significant uncertainties remain. One critical question involves the stability of the warp bubble. In physics, stability means that small perturbations don't cause runaway effects. A ball sitting at the bottom of a bowl is stable, nudge it slightly, and it rolls back to the center. A ball balanced on top of an inverted bowl is unstable. The tiniest disturbance sends it tumbling down. Some preliminary analyses suggest that certain warp bubble configurations might be unstable, meaning that quantum fluctuations or minor variations in the energy field could cause the bubble to collapse or oscillate uncontrollably. Further research is needed to determine whether the new constant velocity design exhibits stable or unstable behavior under realistic conditions. If it's inherently unstable, that doesn't doom the concept, but it means you'd need active stabilization systems constantly monitoring and adjusting the field, adding another layer of complexity. Quantum mechanics introduces additional complications. General relativity, the framework within which warp drives are designed, is a classical theory. It doesn't account for quantum effects, the probabilistic behavior of matter and energy at microscopic scales. For most astronomical applications, this limitation doesn't matter. The Sun, planets, and galaxies are so massive that quantum effects average out. But warp drives operate at the boundary between the macroscopic and quantum regimes. The intense curvature at the bubble boundary, the enormous energy densities involved, these might trigger quantum phenomena that classical general relativity can't predict. Quantum field theory in curved spacetime, an advanced theoretical framework combining quantum mechanics with general relativity, suggests that strong gravitational fields can produce particle creation from vacuum fluctuations. Near black hole event horizons, this leads to Hawking radiation, named after Stephen Hawking, who predicted it theoretically in 1974. A warp bubble's boundary might similarly generate radiation through quantum processes. If this radiation carries away significant energy, it could destabilize the bubble or require even more power input to compensate. These quantum corrections remain speculative because we don't have a complete theory of quantum gravity. String theory, loop quantum gravity, and other approaches attempt to unify quantum mechanics with general relativity, but none has achieved definitive success or experimental confirmation. Until we understand quantum gravity better, we can't definitively say how quantum effects would impact warp drive operation. This represents a fundamental knowledge gap, one that might require revolutionary insights to bridge. Despite these unknowns, incremental progress is possible. Researchers can study analogous systems where space-time curvature effects appear in more accessible contexts. One fascinating area of research involves acoustic black holes, also called dumb holes. In these systems, flowing fluids create regions where sound waves can't escape, analogous to how light can't escape a gravitational black hole. By studying acoustic black holes in laboratory settings, physicists can test predictions about Hawking radiation and other quantum effects without needing actual black holes. Similarly, analog gravity experiments use carefully designed optical or fluid systems to simulate aspects of curved spacetime. Light passing through certain materials with varying refractive indices experiences effects mathematically equivalent to propagating through curved spacetime. These analogues can't test every aspect of warp-drive physics, but they provide valuable insights into how fields behave in exotic geometries. Another research avenue involves gravitational wave astronomy. The LIGO and Virgo detectors, which made the first direct detection of gravitational waves in 2015, observe ripples in spacetime caused by catastrophic events like colliding black holes or neutron stars. These detectors measure spacetime distortions that are astonishingly tiny, far smaller than the diameter of a proton. The technology developed for gravitational wave astronomy, precision measurement of spacetime curvature, could eventually prove relevant for warp drive development. If we ever build even a small-scale prototype warp field generator, we'd need instruments capable of detecting the minute spacetime distortions it produces. Gravitational wave detector technology, refined over decades and now operational, provides exactly that capability. Imagine a tabletop experiment that creates a tiny warp bubble, perhaps only micrometers across, sustained for a fraction of a second. Detecting and characterizing that bubble would require instrumentation derived from gravitational wave research. Such small-scale experiments might seem absurdly distant from actual interstellar spacecraft, but they'd represent crucial proof-of-principle demonstrations, showing that you can manipulate space-time curvature in controlled, predictable ways would validate the underlying physics and provide data to refine theoretical models. It's analogous to how early nuclear physics experiments with tiny amounts of radioactive material eventually led to nuclear reactors and weapons. The scale difference is enormous, but the fundamental physics connects them. Let's consider the energy scales more concretely. Estimates for the energy required by the new warp drive design vary depending on assumptions about bubble size and speed, but one analysis suggests that a bubble large enough to contain a spacecraft moving at 1/10 the speed of light might require mass energy equivalent to roughly Jupiter's mass. Jupiter contains about 318 times Earth's mass. Converting even a small fraction of that to usable energy exceeds anything remotely possible with current technology. For context, the total energy consumption of human civilization in 2020 was approximately 600 exajoules. A joule is the energy needed to lift a small apple 1 meter against Earth's gravity. An exajoule is 10 to the 18th joules, or a billion joules. Now, Jupiter's mass energy using Einstein's E equals mc squared equals approximately 1.8 times 10 to the 42 joules. That's roughly 3 trillion times humanity's annual energy consumption. These numbers are so vast they lose intuitive meaning. Let's approach it differently. The Sun outputs about 3.8 times 10 to the 26 watts of power, which over a year equals about 1.2 times 10 to the 34 joules. To accumulate Jupiter's mass energy worth of power from the Sun's output would take approximately 14 million years. Even if we could build a Dyson sphere, a hypothetical megastructure capturing all of a star's energy output, we'd need millions of years of collection to power a single warp drive flight. This illustrates the challenge clearly. The physics allows warp drives, but the engineering requires capabilities so far beyond our current level that it resembles magic. However, two important points temper this pessimism. First, these energy estimates might decrease significantly as models improve. The initial Alcubierre design required energy equivalent to multiple solar masses. Refinements reduced that to planetary masses. Further optimization might reduce it to asteroid masses or even less. Every order of magnitude reduction makes the problem more tractable. Second, advanced civilizations could potentially harness energy sources we haven't accessed. A Type 2 civilization on the Kardashev scale, a system proposed by Soviet astronomer Nikolai Kardashev in 1964, would control all the energy output of its host star. Type 3 civilizations would harness entire galaxies. By Kardashev's classification, humanity currently ranks around Type 0.7, not even Type 1 yet, which would mean controlling all energy available on Earth, including solar radiation reaching our planet. A civilization even moderately more advanced than ours, perhaps Type 1.5 or 2, might find warp drive energy requirements challenging but manageable. This connects to the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the complete absence of evidence for them. Enrico Fermi famously asked, "Where is everybody?" If the galaxy is billions of years old, if intelligent life arises relatively easily, if technological civilizations expand and explore, why haven't we detected any signs of them? One possible answer to the Fermi paradox is that interstellar travel remains so difficult that even advanced civilizations don't attempt it. The vast distances and enormous energy requirements create an insurmountable barrier. If warp drives or similar technologies prove impossible to develop, then every civilization remains confined to its home system, perhaps sending out radio signals, but never physically traveling between stars. This would explain why we see no evidence of galactic colonization, no megastructures harvesting stellar energy, no signs of vast interstellar empires. Alternatively, if warp drives are achievable, the absence of obvious alien visitors suggests either that we're among the first civilizations to reach this level, which seems statistically unlikely given the universe's age, or that advanced civilizations choose not to make their presence known. Perhaps they observe a cosmic form of the Prime Directive, Star Trek's fictional rule, against interfering with less developed species. Or perhaps intelligence capable of building warp drives also transcends physical exploration, uploading consciousness into digital substrates or pursuing goals we can't even imagine. These philosophical tangents matter because warp drive research forces us to confront deep questions about our cosmic context. Are we alone? If not, what does the silence tell us? If interstellar travel proves fundamentally impossible, what does that mean for humanity's long-term future? If it's possible but enormously difficult, how does that shape our understanding of what civilizations can achieve? Some scientists propose that the absence of obvious extraterrestrial artifacts suggests we might be living in a simulation, a computed reality created by a more advanced civilization. In this view, the apparent fine-tuning of physical laws, the Fermi paradox, and other cosmic mysteries make more sense if our universe is essentially software running on some inconceivable substrate. Warp drives in a simulated universe would just be another set of programmed rules, as arbitrary or constrained as the simulation's designers chose to make them. Most physicists consider simulation arguments interesting but untestable, placing them outside the realm of science proper. Still, they illustrate how breakthrough propulsion research connects to fundamental questions about reality itself. When you're exploring the limits of physical law, you inevitably brush against metaphysics, the study of existence and causation that sits at the boundary between physics and philosophy. Returning to concrete physics, let's examine what the new warp drive model tells us about the nature of space-time. Einstein's general relativity describes space-time as a four-dimensional fabric, 3 dimensions of space and 1 of time, woven together. Mass and energy curve this fabric, and objects follow the straightest possible paths through the curved geometry, which we perceive as gravitational attraction. This geometric picture replaced Newton's idea of gravity as a force acting at a distance. One profound implication of general relativity is that space-time itself is dynamic. It can expand, contract, ripple, and distort. The universe's expansion discovered by Edwin Hubble in 1929 represents space-time itself stretching, carrying galaxies apart. This expansion can occur faster than light because it's not matter moving through space but space itself growing. Distant galaxies recede from us at velocities exceeding light speed due to cosmic expansion, and this violates no physical law. Warp drives exploit this same principle. By creating a region where space-time contracts ahead and expands behind, you achieve effective faster-than-light travel without anything locally moving faster than light. It's cosmic expansion and contraction on demand, a technology that harnesses one of the universe's most fundamental properties. In this sense, warp drives represent applied cosmology, taking phenomena usually observed only on universe-spanning scales and miniaturizing them for propulsion. The mathematics describing cosmic expansion and warp bubbles share a common structure. Both involve metrics, mathematical objects that define distances in curved space-time. The Friedmann-Lemaitre-Robertson-Walker metric describes an expanding universe. The Alcubierre metric describes a warp bubble. Both are solutions to Einstein's field equations under different conditions. By studying one, physicists gain insights applicable to the other. This cross-pollination between cosmology and propulsion research yields unexpected benefits. Theoretical work on warp drives has illuminated aspects of cosmic inflation, the hypothetical exponential expansion of the early universe that occurred in the first tiny fraction of a second after the Big Bang. Inflation explains several otherwise puzzling features of the cosmos, such as why the observable universe appears so uniform in temperature and structure despite regions that should never have been in causal contact. The mechanism driving inflation remains uncertain, but it involves something causing space-time to expand dramatically faster than light for a brief period. Understanding how fields could generate this kind of explosive growth helps physicists develop better inflation models. Conversely, insights from inflation theory inform warp drive research, suggesting possible energy field configurations that might generate the necessary space-time distortions. Another connection involves dark energy, the mysterious component making up approximately 68% of the universe's total mass energy. Dark energy causes cosmic expansion to accelerate, pushing galaxies apart ever faster. We don't know what dark energy is. The simplest explanation is a cosmological constant, an energy density inherent to empty space itself, but other possibilities include dynamic fields that vary over time and space. Some speculative proposals suggest that understanding and manipulating dark energy could provide the power source for warp drives. If dark energy pervades all of space with a positive energy density, perhaps advanced technology could concentrate or redirect it. This remains pure speculation. We don't even understand what dark energy is, much less how to manipulate it. But it illustrates how frontier physics questions interconnect in surprising ways. Dark matter presents another cosmic mystery. This invisible substance makes up about 27% of the universe's mass energy and reveals itself only through gravitational effects on visible matter and light. Galaxies rotate faster than they should based on their visible matter alone, suggesting massive halos of dark matter surround them. Gravitational lensing, where light from distant objects bends around massive structures, shows dark matter's presence throughout the cosmos. Multiple candidates for dark matter exist. Weakly interacting massive particles, or WIMPs, are hypothetical particles that interact only through gravity and the weak nuclear force. Axions are even lighter hypothetical particles proposed to solve problems in quantum chromodynamics, the theory of the strong nuclear force. Primordial black holes formed in the early universe rather than from stellar collapse represent another possibility. Despite decades of experimental searches, we haven't definitively detected dark matter particles directly. Could dark matter play a role in warp drive technology? Probably not directly, since dark matter interacts so weakly with ordinary matter that harnessing it seems impractical. However, understanding what dark matter is and how it behaves gravitationally might inform our general knowledge of space-time manipulation. Every mystery we solve about the universe's fundamental composition potentially opens new technological doors. The interplay between fundamental research and applied technology has driven human progress for centuries. Quantum mechanics, developed in the early 20th century to explain atomic behavior, seemed utterly abstract and impractical, yet it underlies all modern electronics. Transistors, microprocessors, lasers, LED lights, solar panels, MRI machines all depend on quantum principles. Scientists studying atomic spectra in the 1920s never imagined smartphones, yet their research made them possible. Similarly, Einstein developed general relativity to understand gravity and cosmology, not to enable GPS navigation. Yet GPS satellites must account for relativistic effects to function. Time dilation corrections are hard-coded into the system. Without general relativity, GPS would fail within minutes, accumulating errors that would make the technology useless. This demonstrates how even the most theoretical physics can have practical applications, though often in ways nobody anticipates. Warp drive research follows this pattern. Even if we never build an actual warp-capable spacecraft, the effort to understand space-time manipulation will yield insights applicable elsewhere. Improved gravitational wave detectors, new materials capable of withstanding extreme conditions, advances in energy generation and storage, computational methods for solving complex differential equations, all of these could emerge from warp drive research programs. There's also educational value. Pursuing grand challenges inspires students and focuses research communities. The Apollo program, which landed humans on the moon between 1969 and 1972, wasn't primarily about lunar geology. It was a demonstration of technological capability, a unifying national goal that drove innovation across multiple fields. Engineers developed integrated circuits, lightweight materials, and miniaturized computers to meet Apollo's demands. Those technologies then revolutionized industries having nothing to do with spaceflight. A serious, well-funded effort to develop warp drive technology, even knowing success might require centuries, could catalyze similar innovation. Universities would expand programs in relativistic physics and advanced propulsion. Private companies would invest in enabling technologies. Young people would pursue careers in science and engineering, inspired by humanity's boldest dream. Currently, no such massive program exists. Warp drive research receives minimal funding, conducted mainly by small teams at universities and private institutes. This might change as the concept gains legitimacy. The transition from science fiction nonsense to extraordinarily difficult, but not impossible, matters psychologically. It moves warp drives from fantasy to aspiration, from entertainment to engineering. Public perception plays a crucial role. Space agencies like NASA operate on government budgets, which means taxpayers and elected officials must support their missions. If the public views warp drives as realistic long-term goals, that support becomes more likely. Conversely, if people dismiss the concept as fantasy, funding will never materialize. Science communication, explaining both the genuine physics and the formidable challenges, becomes essential. This is why peer-reviewed publications like the 2024 Warp Drive paper matter beyond their scientific content. They provide credibility, demonstrating to policymakers and the public that serious scientists take these ideas seriously. They shift the conversation from "can we?" answered with a definite no to "how might we?" answered with "here are the problems we need to solve." That shift, subtle but profound, opens possibilities that previously seemed closed. Let's discuss another aspect of the warp drive concept, its implications for causality and the structure of space-time. General relativity, for all its elegance, permits solutions that challenge our intuitions about cause and effect. Closed time-like curves, which we mentioned earlier, represent one example. Wormholes, hypothetical tunnels, through space-time connecting distant regions, represent another. Wormholes, if they exist and can be traversed, would offer an alternative to warp drives for covering cosmic distances quickly. Instead of traveling through normal space, you'd take a shortcut through a different region of space-time. The entrance and exit of a wormhole might be light years apart in conventional space, but only meters apart through the tunnel. Traveling through would take seconds or minutes rather than years. The catch, and there's always a catch, is that traversable wormholes also require exotic matter with negative energy density. The throat of the wormhole, the narrowest part of the tunnel, would collapse instantly unless something with negative energy props it open. This is the same fundamental barrier that plagued warp drives until the 2024 research. No one has yet found a way to construct traversable wormholes using only positive energy. Some physicists speculate that wormholes might exist naturally in the quantum foam, the hypothetical turbulent structure of space-time at the Planck scale, which is roughly 10 to the negative 35 meters. At this unimaginably tiny scale, quantum fluctuations might constantly create and destroy microscopic wormholes. These would be far too small and short-lived to traverse, but their existence would demonstrate that space-time topology can be more complex than we typically assume. The Planck scale represents the frontier where quantum mechanics and gravity become equally important. At larger scales, gravity dominates and quantum effects are negligible, which is why general relativity works so well for describing planets, stars, and galaxies. At much smaller scales, quantum mechanics dominates and gravity is negligible, which is why quantum field theory successfully describes particle physics. But at the Planck scale, both forces matter equally, and we lack a complete theory to describe what happens. String theory attempts to bridge this gap by proposing that fundamental particles aren't point-like, but rather tiny, vibrating strings. Different vibration modes correspond to different particles. In this framework, gravity emerges naturally, and space-time itself might be a secondary phenomenon arising from more fundamental quantum relationships. If string theory is correct, understanding warp drives and wormholes might require understanding string dynamics at energy scales billions of times higher than anything we can produce in particle accelerators. Loop quantum gravity, an alternative approach, quantizes space-time itself, proposing that space and time are granular at the Planck scale rather than continuous. In this view, space-time consists of discrete units, atoms of space in a sense, connected in networks that give rise to the smooth geometry we observe at larger scales. Manipulating these fundamental space-time structures might be necessary for creating stable warp bubbles or wormholes. Both string theory and loop quantum gravity remain incomplete and experimentally unverified. They make predictions about phenomena at energy scales and length scales far beyond current technology's reach. Testing these theories directly might require particle accelerators the size of galaxies. Indirect tests looking for subtle effects in cosmological observations or precision measurements continue, but so far neither theory has achieved definitive confirmation. This brings us to a humbling realization. We're trying to engineer technologies that manipulate space-time using theories we don't fully understand. It's analogous to attempting to build microprocessors while still uncertain about quantum mechanics. The fact that engineers successfully created semiconductors actually helped confirm quantum theory, providing experimental validation that pure theory couldn't achieve alone. Similarly, attempting to build even primitive space-time manipulation devices might teach us things about quantum gravity that thought experiments never could. Let's shift focus to consider what a real warp drive spacecraft might look like. Science fiction often depicts sleek vessels with glowing rings or nacelles, artistic choices driven by visual aesthetics rather than physics. The actual design would depend entirely on how the warp field generator functions. If you need enormous energy densities concentrated in specific geometric patterns, the spacecraft might resemble a power plant more than a rocket, all generators, capacitors, and field coils, with the crew habitat as an afterthought. The field generator would likely surround the habitable section, creating the warp bubble that encompasses the entire vessel. You'd want the bubble boundary as far from crew areas as possible to minimize exposure to intense gravitational fields and any radiation produced at the interface. The spacecraft might be spherical or cylindrical, shapes that naturally accommodate symmetric field configurations. Shielding would be critical. Even though the warp bubble protects you from needing to travel through space at relativistic speeds, the boundary itself represents an extreme environment. Intense gravitational gradients, possible quantum particle production, accumulated matter and radiation from the interstellar medium, all of these pose hazards. Materials science would need to advance dramatically to create structural components capable of withstanding these conditions without degrading or failing catastrophically. Radiation shielding already challenges conventional spacecraft design. Cosmic rays, high-energy particles from supernovae and other violent astrophysical events constantly bombard spacecraft. On Earth, our atmosphere and magnetic field protect us. In space, particularly beyond Earth's magnetosphere, radiation becomes a serious concern for both electronics and biological organisms. Long-duration missions to Mars must address how to shield astronauts from radiation exposure that increases cancer risk and can damage the central nervous system. Warp drives might actually help with radiation, since the compressed space-time ahead could deflect incoming particles around the bubble. However, the accumulated radiation at the bubble boundary could itself become dangerous, especially during formation and collapse of the warp field. Careful analysis would be needed to understand all radiation sources and design appropriate countermeasures. Life support systems for interstellar missions present another engineering challenge. Even with warp drives making trips faster, journeys to nearby star systems might take weeks or months. Closed-loop life support, where you recycle air, water, and nutrients indefinitely, becomes essential. The International Space Station recycles about 90% of water and generates oxygen by electrolyzing water into hydrogen and oxygen. For true long-duration missions, you'd need to approach 100% recycling efficiency. Growing food in space adds complexity but also benefits. Plants produce oxygen, consume carbon dioxide, and provide fresh nutrition. Psychological benefits of tending gardens and eating fresh food matter too. Experiments on the ISS and in enclosed habitats on Earth have demonstrated various approaches to space agriculture, from hydroponic systems to specialized growth chambers. A warp-capable spacecraft would likely incorporate extensive life support gardens, creating a miniature ecosystem. Gravity, or rather its absence, affects human health significantly. Astronauts on the ISS experience bone density loss, muscle atrophy, fluid redistribution, causing vision problems, and immune system changes. Missions lasting months or years require either artificial gravity through rotation or highly effective countermeasures like intensive exercise regimens. A rotating section of the spacecraft could provide Earth-like gravity, though integrating rotation with warp field geometry might introduce complications. Navigation systems would be unlike anything in current spacecraft. You'd need incredibly precise knowledge of your position, velocity, and the space-time curvature you're generating. Inertial navigation, which works by measuring acceleration and integrating to determine position, might not function reliably inside a warp bubble where space-time itself is distorted. External references like distant quasars could provide fixed points for navigation, but detecting them through the bubble boundary presents challenges. Communication represents yet another hurdle. How do you send signals from inside a warp bubble to the outside universe or receive messages from home? If the bubble creates a causally disconnected region, electromagnetic signals can't pass through normally. You might need to periodically drop out of warp to communicate or develop entirely new communication methods that exploit the warp field itself, perhaps modulating the bubble in ways that create detectable gravitational wave signatures. These practical considerations might seem mundane compared to the physics of space-time manipulation, but they're equally essential for actual missions. History is full of ambitious technologies that succeeded technically, but failed practically due to overlooked details. The Concorde supersonic airliner could cross the Atlantic in half the time of conventional jets, but proved economically unviable. Nuclear-powered aircraft engines were developed and tested in the 1950s and 60s, but abandoned because the radiation shielding needed made them impractically heavy. For warp drives to transition from theoretical possibility to operational reality, engineers must solve countless mundane problems alongside the spectacular ones. This is why aerospace development typically proceeds incrementally, each generation of spacecraft slightly more capable than the last, learning from experience and building institutional knowledge. Jumping straight from chemical rockets to warp drives would be like going from horse-drawn carriages to supersonic jets without inventing the internal combustion engine first. A more plausible development path might involve intermediate propulsion technologies. Nuclear fusion rockets, for instance, could potentially reach 10 to 20% of light speed, making interstellar missions feasible within human lifetimes to the nearest stars. These would still take decades but represent a massive improvement over current capabilities. Developing fusion propulsion would also advance our ability to generate and control enormous energy densities, a skill directly relevant to warp drives. Antimatter rockets represent another intermediate step. While antimatter production remains fantastically inefficient and expensive, using roughly 10 billion times more energy to create than you get back, future breakthroughs might improve efficiency. An antimatter rocket carrying just grams of antimatter could theoretically achieve relativistic speeds. The engineering challenges of containing antimatter safely and directing the annihilation energy efficiently for propulsion are formidable but might be more tractable than warp drives. Laser sail technology offers yet another approach. Powerful ground-based or space-based lasers could accelerate lightweight, reflective sails to significant fractions of light speed. The breakthrough Starshot initiative, announced in 2016 and backed by physicist Stephen Hawking and investor Yuri Milner, aims to demonstrate this concept. The plan involves sending thousands of tiny spacecraft, each weighing just grams, to Alpha Centauri using laser acceleration. If successful, these probes could reach their destination in approximately 20 years. Breakthrough Starshot faces enormous technical challenges. The lasers need to deliver gigawatts of power focused precisely on centimeter-scale sails, moving at thousands of kilometers per second. The probes must survive intense acceleration, radiation, and impacts with interstellar dust particles. Communication from over 4 light-years away using tiny transmitters with milliwatts of power pushes the limits of receiver sensitivity. But unlike warp drives, none of these challenges violates known physics. They're all extremely difficult engineering problems rather than fundamental impossibilities. If breakthrough Starshot succeeds, even partially, it would represent humanity's first true interstellar mission, our first physical presence in another star system. The scientific and cultural impact would be profound. We'd have images and data from worlds that currently exist only as points of light in telescopes. We'd know whether planets orbiting Alpha Centauri possess atmospheres, water, or any signs of life. That knowledge would reshape our understanding of our place in the cosmos. Projects like Breakthrough Starshot also develop technologies applicable to warp drives. Precision optics, high-power lasers, ultra-lightweight materials, miniaturized electronics capable of surviving extreme conditions, all of these capabilities would benefit any advanced propulsion program. This is why pursuing multiple approaches simultaneously makes sense. Each avenue of research informs others, creating a rich ecosystem of innovation. Let's return to the fundamental physics for a moment and consider an important question. Why does the new warp drive design work when previous versions required exotic matter? The answer lies in the geometry of the space-time distortion. Previous models created what physicists call a thin shell configuration, where space-time curvature changes abruptly over a very short distance. These sharp transitions are what necessitated negative energy. The new design uses a thick shell with gradual transitions. By spreading the curvature change over a larger region and carefully tuning the energy density distribution, the researchers eliminated regions where negative energy would be required. It's similar to how a gentle slope is easier to climb than a cliff. The same vertical distance is covered, but distributing it over a longer horizontal distance makes it manageable. Mathematically, this involves choosing a specific metric, a formula describing distances in the curved spacetime that satisfies Einstein's field equations while also satisfying energy conditions. The field equations relate spacetime curvature to the stress-energy tensor, a mathematical object encoding how matter and energy are distributed. Finding metric solutions that produce warp bubble behavior while keeping the stress-energy tensor physically reasonable is the core challenge. The researchers employed numerical methods using computers to search through vast parameter spaces of possible solutions. They varied the shape of the energy distribution, the thickness of the shell, the transition rates between different regions, systematically exploring configurations until finding ones that satisfied all constraints. This computational approach complements analytical methods, where you derive solutions by hand using mathematical techniques. Many problems in physics are too complex for analytical solutions but yield to numerical computation. The advent of powerful computers has revolutionized theoretical physics. Einstein worked out general relativity with pen, paper, and extraordinary geometric intuition. Today's physicists can simulate black hole collisions, model the early universe's evolution, and explore exotic space-time geometries using supercomputers performing trillions of calculations per second. These simulations don't replace human insight, they amplify it, allowing researchers to test ideas that would be impossible to evaluate otherwise. Artificial intelligence and machine learning are beginning to contribute as well. Neural networks can recognize patterns in complex data that humans might miss. Some researchers are training AI systems to propose new solutions to physical equations, essentially automating part of the discovery process. An AI trained on thousands of known solutions might generate novel configurations that physicists can then analyze and refine. This collaboration between human creativity and machine computational power represents the future of theoretical research. Imagine an AI system tasked with optimizing warp bubble geometry. You'd specify your constraints: positive energy only, stable configuration, maximum velocity, minimal energy requirement. The AI would explore millions of possible designs, evaluating each against your criteria, gradually converging on optimal solutions. It might discover configurations that human intuition would never suggest, but that nevertheless satisfy all physical requirements. This approach could accelerate warp drive research significantly. However, AI has limitations. It can't understand physics in the deep sense that humans do. It recognizes patterns and optimizes functions, but doesn't grasp why certain configurations work. Human physicists must interpret AI suggestions, verify they're physically meaningful, and understand the principles underlying successful designs. The synergy between AI capability and human understanding might unlock breakthroughs neither could achieve alone. Let's consider the historical context of breakthrough propulsion concepts. Throughout the 20th century, visionaries proposed revolutionary transportation technologies. Some succeeded, many failed. Robert Goddard, working in the early 1900s, faced ridicule when he proposed liquid-fueled rockets capable of reaching space. A famous New York Times editorial in 1920 mocked him, stating that rockets couldn't work in space's vacuum because they'd have nothing to push against. The Times formally corrected this error in 1969, the day after Apollo 11 launched toward the Moon. This episode illustrates two important lessons. First, even educated people can be wrong about what physics allows when dealing with unfamiliar concepts. Second, visionaries working on seemingly impossible technologies sometimes succeed spectacularly. Goddard's rockets did work, of course, and they transformed civilization. We should be cautious about declaring any concept impossible if the basic physics permits it. Nuclear propulsion provides another instructive example. In the 1950s and 60s, Project Orion explored spacecraft propelled by nuclear explosions. The design involved detonating atomic bombs behind a massive pusher plate with shock absorbers transferring momentum to the spacecraft. This sounds absurd, yet the physics works. Detailed engineering studies showed Orion spacecraft could reach several % of light speed, enabling interstellar missions within a few centuries. Project Orion was cancelled not because the concept was flawed, but due to political concerns about nuclear testing and the Partial Nuclear Test Ban Treaty of 1963. The technology worked in principle and likely in practice, but social and political factors prevented its development. This demonstrates that technological feasibility isn't the only factor determining what gets built. Economic viability, political will, environmental concerns, and public acceptance all matter. Warp drives will face similar non-technical challenges even if the physics and engineering eventually work out. The energy requirements might necessitate technologies like fusion reactors or antimatter production that carry risks and controversy. Manipulating space-time could have unintended consequences we don't foresee. Public fear, regulatory barriers, and competing priorities might delay or prevent development regardless of technical readiness. On the other hand, compelling motivation can overcome enormous obstacles. The Manhattan Project, which developed atomic weapons during World War II, mobilized unprecedented resources and achieved what many thought impossible in just a few years. The Apollo program, driven by Cold War competition, landed humans on the Moon within a decade of President Kennedy's challenge. When societies commit fully to ambitious technological goals, progress can be astonishingly rapid. What might motivate similar commitment to warp drive development? Several scenarios seem plausible. Discovery of life on nearby exoplanets would create intense desire to visit and study it directly. Detection of artificial signals from another civilization would drive efforts to establish contact. An asteroid impact threat or other existential risk might spur development of technologies enabling rapid space travel and potential evacuation. Or perhaps as Earth's resources become constrained and climate challenges intensify, the promise of accessing abundant resources throughout the galaxy could provide motivation. Alternatively, development might proceed gradually without single dramatic catalysts, driven by accumulating knowledge, advancing technology, and growing human presence in space. As we establish permanent settlements on the Moon and Mars, as asteroid mining becomes economically viable, as fusion power becomes practical, our capabilities expand. Each generation's impossible becomes the next generation's routine. Warp drives might simply be another step in this progression, achieved when sufficient prerequisite technologies mature. The role of private enterprise deserves consideration. Historically, governments funded most space exploration through agencies like NASA, the Soviet space program, ESA in Europe, and more recently, China's space agency. But the 21st century has seen dramatic growth in private spaceflight. SpaceX has revolutionized launch costs with reusable rockets. Blue Origin is developing lunar landers and orbital systems. Numerous smaller companies work on satellite constellations, space tourism, and in-space manufacturing. Private funding follows profit potential. Warp drives have no obvious near-term commercial application, making private investment unlikely until the technology matures significantly. However, visionary billionaires have funded speculative long-term research before. The breakthrough initiatives, including Starshot, receive private funding. If warp drive research demonstrates steady progress, private capital might eventually flow into it, especially if spin-off technologies prove commercially valuable. Universities and research institutions will likely drive early-stage warp drive research, conducting theoretical studies, performing simulations, and perhaps eventually building small-scale experimental apparatus. Government funding through agencies like NASA, the National Science Foundation, or equivalents in other countries would support this work. As concepts mature and demonstrate viability, larger investments from government programs or private consortia might follow. International collaboration seems inevitable for any serious warp drive development program. The cost and complexity would likely exceed any single nation's capacity or willingness to fund alone. A project comparable to the International Space Station or the International Thermonuclear Experimental Reactor, ITER, a multinational fusion research facility under construction in France, provides a plausible model. Multiple nations and space agencies could contribute expertise, funding, and resources toward a common goal. Such collaboration faces challenges, political tensions, competing priorities, and differing technical approaches can complicate international projects. ITER, for example, has experienced significant delays and cost overruns partly due to coordination difficulties among its 7 member entities. However, successful collaboration also demonstrates that nations can work together on ambitious scientific endeavors despite political differences. The benefits of pooling resources and talent often outweigh the coordination costs. Education will play a crucial role. Developing warp drive technology requires a deep pool of trained physicists, engineers, and mathematicians. This means sustained investment in STEM education, from elementary schools through graduate programs. Countries that prioritize science and technology education position themselves to contribute to and benefit from breakthrough innovations. Brain drain, where talented individuals migrate to countries with better opportunities, means that education investment in one nation can benefit others, creating global incentive to support scientific training. Public engagement matters too. Science communication, helping the general public understand both the excitement and the challenges of cutting-edge research, builds support for funding and attracts young people to scientific careers. Documentaries, educational videos, planetarium shows, science museums all contribute to creating a scientifically literate society that values research and exploration. This channel aims to be part of that effort, making complex cosmology and physics accessible and inspiring. Let's consider some alternative approaches to faster-than-light travel that don't involve warp drives. One concept involves manipulating the speed of light itself. In vacuum, light travels at roughly 300 million meters per second, but in materials, light slows down. The refractive index of a material determines how much slower. Water has a refractive index of about 1.33, meaning light travels about 75% as fast in water as in vacuum. Some materials, under special conditions, can slow light dramatically. Researchers have reduced light speed to just 17 meters per second in ultra-cold atomic gases. Others have even stopped light completely, storing its energy in atomic excitations and then releasing it. These experiments suggest that light's speed isn't as absolute as we typically think. However, this applies only to light propagating through matter. The fundamental speed limit of causality, the maximum speed at which information can travel, remains constant. You can't exploit slow light to travel faster than that fundamental limit. Another speculative concept involves quantum entanglement. When particles become entangled, measuring one instantly affects the other, regardless of distance. Einstein called this spooky action at a distance and found it troubling. Experiments have confirmed that entanglement is real. Measuring one particle's property instantly determines its partner's property, even across large distances. However, you can't use entanglement to send information faster than light. The measurement results appear random until you compare them, and that comparison requires conventional slower-than-light communication. Some physicists have explored whether entanglement might enable exotic propulsion or communication methods, but most consider this unlikely. The fundamental theorem prohibiting faster-than-light signaling through quantum mechanics, called the no-signaling theorem, appears robust. Still, as our understanding of quantum mechanics deepens, particularly regarding quantum field theory and quantum gravity, surprising connections might emerge. Tachyons represent another theoretical concept. These hypothetical particles would travel faster than light at all times, unable to slow down below light speed, just as normal matter can't accelerate above it. Tachyons have imaginary mass in the mathematical sense, not immaterial but having a mass value that's a multiple of the square root of -1. No experiment has ever detected tachyons, and most physicists doubt they exist. If they did, they'd create severe causality problems, potentially allowing effects to precede causes. Every alternative to warp drives faces fundamental challenges rooted in special relativity and causality. Warp drives avoid these problems by not actually moving through space faster than light locally. They manipulate spacetime itself, exploiting general relativity's flexibility. This is why, among all faster-than-light concepts, warp drives have the strongest theoretical foundation. They don't violate relativity, they apply it creatively. The philosophical implications of achieving interstellar travel deserve reflection. For over 100,000 years, humans have gazed at stars with wonder and longing, inventing mythologies to explain them, navigating by them, gradually discovering their true nature as distant suns. Only in the last century did we develop the physics suggesting travel between stars might be possible, and only in the last few years has that possibility acquired mathematical rigor and physical plausibility. If humanity achieves interstellar travel, whether through warp drives or other means, we cross a threshold that divides our existence into before and after. Before, we were confined to a single star system, able to observe the universe but not truly explore it. After, we become a spacefaring species in the fullest sense, capable of physically reaching other worlds, touching the surface of planets orbiting distant suns, perhaps even encountering other forms of life. This transformation would rank among the most significant in our species' history, comparable to when our ancestors first left Africa, or when agriculture enabled civilization. The challenges facing us extend beyond technology. Interstellar missions raise profound ethical questions. If we discover life on other worlds, even microbial life, how should we interact with it? Earth's history of exploration is marked by conquest, exploitation, and the devastating impact of contact between civilizations at different technological levels. We must approach cosmic exploration with humility and wisdom, guided by principles that protect both ourselves and whatever we might encounter. Planetary protection protocols already exist for missions within our solar system. When we send probes to Mars or Europa, Jupiter's moon with a subsurface ocean, we sterilize them carefully to avoid contaminating these worlds with Earth microbes. The goal is preserving any indigenous life for scientific study and preventing our biology from overwhelming theirs. These protocols would need expansion and refinement for interstellar missions, where the stakes might be even higher. Then there's the question of who represents humanity in space. Early space exploration was dominated by governments, specifically Cold War superpowers asserting national prestige. The Outer Space Treaty of 1967 established that no nation can claim sovereignty over celestial bodies, that space exploration should benefit all humanity, and that weapons of mass destruction shouldn't be placed in orbit. These principles have generally held, though commercial space activities are testing their boundaries. For interstellar missions, particularly those involving warp drives requiring enormous resources, governance structures would need to be international or even global in scope. Who decides where we go? How are crew members selected? What protocols govern first contact with alien life or artifacts? These questions have no easy answers, but addressing them before we have the capability is wiser than confronting them amid crisis or opportunity. Science fiction has explored these themes extensively, offering cautionary tales and inspiring visions. Star Trek's United Federation of Planets presents an optimistic future where diverse species cooperate peacefully, guided by principles of exploration and mutual understanding. The Prime Directive prohibits interference with less developed civilizations, recognizing that contact can be harmful. Other stories depict darker scenarios: exploitation, warfare, biological or cultural contamination, the loneliness of vast distances, and the psychological toll of isolation. Fiction can't predict the future, but it helps us think through possibilities and consequences. Many scientists credit science fiction with inspiring their careers. Carl Sagan, Neil deGrasse Tyson, Michio Kaku, and countless others cite science fiction stories as formative influences. The genre creates a space where we can imagine futures and work backward to determine what would be required to achieve them. Warp drives themselves moved from fiction to serious research, partly because stories made the concept familiar and desirable. This cultural dimension matters. Technologies succeed not just because they're possible, but because people want them enough to invest resources in developing them. Solar power, electric vehicles, and reusable rockets all faced skepticism and market resistance before reaching viability. Visionaries who believed in these technologies, who communicated their potential compellingly, helped overcome inertia and attract the support needed for development. Warp drives will need similar advocates, people who can bridge the gap between abstract physics and public imagination. Let's discuss the timeline more concretely. Where might we be in 10 years, 50 years, a century? In the next decade, warp drive research will likely remain theoretical and computational. Physicists will refine models, exploring variations on the constant velocity design and seeking solutions that reduce energy requirements further. They might discover new configurations that allow acceleration and deceleration without exotic matter, or find ways to stabilize warp bubbles against perturbations. Small-scale experimental work might begin. Not warp bubbles large enough to move spacecraft, but perhaps tiny distortions in space-time that can be detected with sensitive instruments. These proof-of-concept experiments would validate theoretical predictions and identify unexpected phenomena. They'd be analogous to early 20th century atomic physics experiments, working with individual particles and tiny energies, but establishing the foundations for later nuclear technology. In 50 years, assuming steady progress and growing investment, we might have laboratory-scale warp field generators. These would create measurable space-time distortions, perhaps moving microscopic objects in controlled ways. The energy requirements would still far exceed anything practical for propulsion, but the demonstration that we can manipulate space-time deliberately would mark a crucial milestone. It would also likely reveal practical problems that theory didn't anticipate, spurring new research directions. Materials science would advance significantly by mid-century. We might have stable room temperature superconductors, enabling lossless electrical transmission and powerful electromagnets without cryogenic cooling. Metamaterials with designer properties programmed at the molecular level could provide unprecedented control over electromagnetic fields. Fusion power might be commercially viable, providing abundant clean energy. These enabling technologies don't directly create warp drives, but make them progressively less impossible. By the end of the century, perhaps the late 2100s, a first experimental warp-capable vehicle might be under construction. This wouldn't be ready for interstellar missions. It would be a testbed, maybe operated remotely in deep space where its operation poses no risk to Earth or inhabited areas. Early tests might achieve only modest effects, compressing and expanding spacetime by tiny fractions, moving the test vehicle short distances at speeds still well below light speed. These tests would face numerous failures, components would malfunction, calculations would prove incorrect, unexpected instabilities would emerge. This is how engineering works, especially pioneering engineering. The Wright brothers' early aircraft crashed repeatedly. Rocket pioneers like Goddard and Wernher von Braun experienced countless explosive failures before achieving success. Each failure teaches lessons that increase the probability of future success. Over decades of testing, refinement, and incremental improvement, warp drive technology would mature. Energy requirements would decrease as designs optimize. Operational reliability would increase as we understand failure modes and implement safeguards. Eventually, perhaps in the 22nd or 23rd century, the first crewed warp flight might occur. A brave crew would board a vessel powered by technologies their ancestors could barely imagine, activate the warp field generator, and experience something no human ever had, traveling faster than light while time flows normally. This timeline is speculative, of course. Progress could be faster if unexpected breakthroughs occur, or if society prioritizes warp drive development as a civilizational goal. It could be slower if the challenges prove more intractable than anticipated, or if humanity faces crises that divert attention and resources elsewhere. It's also possible, though I believe unlikely, that we'll discover fundamental barriers making warp drives impossible, despite the theoretical physics allowing them. What destinations might early warp missions target? Proxima Centauri at 4.2 light-years is the obvious first choice. This red dwarf star hosts at least 2 confirmed planets, including Proxima Centauri b, an Earth mass world in the habitable zone. Recent observations suggest it might have oceans and potentially even a thin atmosphere. Whether life exists there remains unknown, but the possibility alone makes it compelling. Alpha Centauri A and B, a binary star system with Proxima as a distant companion, lie 4.4 light-years away. These Sun-like stars could host Earth-like planets, though we haven't detected any yet. The system's similarity to our own solar system makes it scientifically fascinating. Missions to Alpha Centauri could search for planets we've missed and study how binary star systems influence planetary formation and evolution. Barnard's star, 6 light-years away, is another red dwarf with at least 1 confirmed planet. The planet appears too cold for life as we know it, orbiting beyond what we'd consider the habitable zone. But studying frozen worlds around other stars would teach us about planetary diversity and the limits of habitability. We might discover exotic life forms adapted to conditions we consider hostile. TRAPPIST 1, 39 light-years away, offers perhaps the most exciting destination. 7 Earth-sized planets, 3 potentially habitable, all orbiting a small, cool star. The system is older than our Sun, meaning life, if it arose there, had time to evolve complexity. A single warp mission could visit multiple potentially habitable worlds, dramatically increasing our chances of finding life. The discoveries made there could revolutionize biology, philosophy, and our understanding of our place in the universe. Tau Ceti, nearly 12 light-years away, is a sun-like star with multiple confirmed planets, some possibly in the habitable zone. It's been a favorite target in the search for extraterrestrial intelligence because its similarity to our Sun suggests it could host advanced life. A mission there would assess habitability and search for any signs of technology or civilization. These are just the nearest targets. Within 100 light-years, thousands of potentially interesting systems await exploration. Planets around orange dwarf stars, which live longer than Sun-like stars, might be especially promising for life since they offer stable environments for billions of additional years. Some might host civilizations that arose earlier than ours and achieved technological sophistication we can only imagine. The prospect of encountering extraterrestrial intelligence raises questions that humanity has pondered for generations. Are we alone in the universe? If not, what are alien civilizations like? Would we recognize their technology, their communication, their very existence? Would they be peaceful or hostile? How would contact change us psychologically, culturally, spiritually? Ceti, the search for extraterrestrial intelligence, has monitored radio signals since the 1960s, looking for artificial patterns that would indicate technological civilizations. Despite decades of effort, we've detected nothing definitive. This could mean intelligent life is extraordinarily rare, perhaps unique to Earth, or it might mean we're looking in the wrong places, at the wrong frequencies, or that advanced civilizations use communication methods we haven't imagined. If we develop warp drives, we wouldn't need to detect alien signals to find aliens. We could visit potentially habitable planets directly, searching for biosignatures or technosignatures in person. The advantage of physical presence over remote observation is overwhelming. We could analyze atmospheres in detail, explore surfaces, search for ruins or artifacts, perhaps even find living civilizations. The probability of success would increase dramatically compared to passive observation from Earth. However, interstellar exploration, even with warp drives, would require immense patience. Even if you can travel at several times the speed of light, reaching targets hundreds of light-years away requires decades or centuries. Mission planning timelines would span generations. Crews might need to be frozen in suspended animation, or missions might be multi-generational, with descendants completing journeys their ancestors began. These challenges pale compared to exploring without warp drives, where journeys require thousands or millions of years, but they remain significant. The longest space mission to date, Voyager 1, has operated for 47 years. Mars missions currently under planning expect to last 2 to 3 years. Extending human spaceflight to decades or centuries demands solving numerous biological, psychological, and engineering problems. Artificial intelligence might play a major role. Autonomous spacecraft capable of self-repair, decision-making, and even reproduction could explore the galaxy without requiring human crews. These von Neumann probes, named after mathematician John von Neumann, who studied self-replicating machines, could visit a star system, gather resources, build copies of themselves, and send those copies to additional systems. Over millions of years, a single self-replicating probe could explore the entire galaxy. Ethical questions arise here too. Should we release self-replicating machines into the cosmos? What if they malfunction, becoming destructive rather than exploratory? What if they encounter alien civilizations or ecosystems? The precautionary principle suggests moving slowly and carefully with technologies that could have irreversible consequences. Perhaps the solution involves combining approaches, sending AI probes to conduct preliminary surveys, followed by crewed missions using warp drives to locations identified as particularly interesting. This staged exploration strategy balances caution with ambition, allowing us to gather information before committing human lives to long, dangerous journeys. The AI scouts could spend decades or centuries cataloging planets, analyzing atmospheres, and searching for signs of life, sending data back to Earth where scientists would prioritize destinations for follow-up missions. This brings us to the question of data transmission. Even with warp-drive spacecraft, communication faces the light-speed barrier. If you travel to a star system 40 light-years away, any message you send back to Earth takes 40 years to arrive. Your family, colleagues, and civilization continue aging while you explore. This temporal disconnect creates profound challenges for maintaining cultural and personal connections across interstellar distances. Some theoretical proposals suggest using quantum entanglement for instantaneous communication, but as mentioned earlier, this doesn't work. The no-signaling theorem prevents faster-than-light information transfer through entanglement. Unless we discover entirely new physics that permit superluminal communication, interstellar missions will operate with significant communications delays. Mission protocols would need to grant spacecraft commanders substantial autonomy, since consulting Earth for decisions would be impractical when responses take decades. This isolation might actually benefit deep space missions in some ways. Crews would develop strong internal cohesion and self-reliance, qualities essential for survival far from home. Historical analogues include early ocean voyages, Arctic expeditions, and submarine patrols, all situations where crews operated independently for extended periods. Psychological screening, team building, and careful mission design can help people cope with isolation and confinement. The cultural impact of discovering alien life, even microbial life, would be immeasurable. Every organism on Earth shares a common biochemistry and evolutionary history. We're all related, descendants of the first self-replicating molecules that appeared billions of years ago. Finding life with a different biochemical basis, using different amino acids or even different information storage molecules than DNA and RNA, would prove that life can arise independently and take forms we haven't imagined. If we discover technological civilizations, the implications become even more profound. We'd learn that intelligence and technology aren't unique to humanity, that the universe might be rich with minds and cultures. This could be profoundly humbling, placing human history and achievements in cosmic context. Alternatively, if we explore hundreds of potentially habitable worlds and find only Earth hosts intelligent life, that would be equally significant, suggesting that consciousness might be extraordinarily rare and precious. The theological and philosophical implications would reverberate through every culture. Major religions would need to grapple with humanity's place in a cosmos populated by other intelligent beings. Some theological frameworks already accommodate this possibility, others would require substantial reinterpretation. Secular philosophies would also face challenges, reconsidering questions about consciousness, meaning, and purpose in light of cosmic plurality. Science fiction often depicts first contact scenarios, exploring how different contact circumstances might unfold. Sometimes aliens are beneficent, sharing knowledge and technology. Sometimes they're hostile, seeing humanity as a threat or resource. Often they're simply indifferent, pursuing goals incomprehensible to us. Reality could match any of these or present scenarios we haven't conceived. Protocols for contact exist. The Ceti post-detection protocol outlines steps to take if we receive an artificial signal from space: verification, notification of authorities and the United Nations, public announcement, and international consultation before responding. For physical contact using warp drives, more detailed protocols would be essential, covering everything from quarantine procedures to diplomatic frameworks. Quarantine deserves special attention. Biological contamination could flow in both directions. Earth microbes could devastate alien ecosystems that never evolved defenses against them. Conversely, alien microorganisms could threaten Earth's biosphere. Even if life forms are too biochemically different to directly infect each other, They might still disrupt ecosystems or carry unforeseen dangers. Strict quarantine protocols, perhaps involving isolation facilities in space rather than bringing samples directly to Earth, would be prudent. The economic dimension of interstellar exploration raises interesting questions. What makes exploration worthwhile from a resource perspective? Scientific knowledge has value, but it's difficult to monetize directly. Historical exploration often sought trade routes, resources, or territory. None of these apply obviously to interstellar missions where transport costs would be astronomical. However, some resources might justify the expense. If we discover planets with rare elements or materials that don't exist naturally on Earth, extracting and returning them could be valuable. Information itself could be valuable, particularly if we encounter advanced civilizations willing to share technology. Patents on alien biotech or manufacturing processes could generate enormous wealth, but these are speculative justifications, uncertain returns on massive investments. More likely, early interstellar missions would be funded for scientific and civilizational reasons rather than economic ones. The knowledge gained, the expansion of humanity's presence beyond one star system, the potential discovery of life, these intangible benefits would justify the cost, just as Antarctic research stations and space telescopes are justified despite producing no direct economic return. Society supports basic research because knowledge has inherent value, and because today's pure science often becomes tomorrow's transformative technology. The development of warp drive technology would also produce numerous spin-off benefits. Advances in energy generation, materials science, precision measurement, computational methods, and many other fields would emerge from the research effort. These would find applications far beyond propulsion, improving life on Earth in ways we can't fully predict. This pattern has repeated throughout technological history, where ambitious projects catalyze innovation across multiple domains. GPS technology emerged from military navigation needs. The Internet began as a Defense Department communications network. Microwave ovens descended from radar development. Memory foam and cordless tools came from the space program. Attempting to build warp drives would similarly generate unexpected technologies that benefit society broadly. Let's consider the long-term trajectory if humanity successfully develops interstellar travel. Over centuries and millennia, we might establish settlements on habitable planets around other stars. These colonies would gradually diverge culturally and perhaps even biologically from Earth as they adapt to local conditions. Eventually, they might become independent civilizations, maintaining cultural connections to humanity but pursuing their own destinies. This prospect of a diverse, multi-system human civilization spanning the galaxy represents an inspiring vision. It's also a form of insurance against existential risks. Currently, all of humanity resides in one star system. A sufficiently large asteroid impact, nearby supernova, or even self-inflicted catastrophe like nuclear war or engineered pandemic could potentially end human civilization or even cause our extinction. Spreading across multiple star systems would make us resilient to local disasters, ensuring that no single event could destroy humanity entirely. This motivation, survival insurance, might ultimately drive interstellar expansion more strongly than scientific curiosity or economic incentives. We're beginning to recognize that Earth's resources are finite and that our actions can have planetary-scale consequences. Climate change, biodiversity loss, resource depletion, these challenges prompt some to advocate for space expansion as a long-term solution. While we must address Earth's problems directly, developing the capability for interstellar travel provides options for our distant descendants. However, we must avoid the moral hazard of treating Earth as expendable. Some critics of space exploration argue that we should fix problems at home before venturing to the stars. This presents a false dichotomy. We can and should do both, addressing immediate challenges while also investing in long-term capabilities. The resources devoted to space research are tiny compared to global GDP. NASA's budget, for instance, represents less than 0.5% of US federal spending. Reallocating space funding wouldn't solve terrestrial problems, and abandoning space would sacrifice enormous potential benefits. The question isn't whether to explore space or fix Earth, it's how to balance immediate needs against long-term investments. This requires wisdom, careful prioritization, and recognition that some problems need solutions spanning decades or centuries. Warp drive research exemplifies long-term investment. No one expects immediate practical applications, but centuries from now, descendants might look back on today's theoretical work as the foundation for technologies that define their civilization. Education and inspiration represent another crucial aspect. Young people learning about warp drives, even knowing they won't be realized in their lifetimes, might pursue careers in physics, engineering, or related fields. The sense that humanity has ambitious long-term goals, that we're working toward capabilities that seem almost magical, motivates people to contribute. This aspirational quality of space exploration shouldn't be dismissed as mere romanticism. It's a real factor in attracting talent and maintaining societal support for science. Many breakthrough technologies emerged from research pursued for inspirational rather than practical reasons. Particle accelerators, which gave us detailed understanding of matter's fundamental structure, were built to answer abstract questions about quarks and bosons, not to develop applications. Yet they led to technologies like PETI scanners that save lives daily. Similarly, research into general relativity was pure physics with no obvious applications, yet GPS navigation now depends on it. Warp drive research follows this tradition of curiosity-driven science that unexpectedly yields practical benefits. Let's return one more time to the fundamental physics and consider what unresolved questions remain. The constant velocity warp drive design represents major progress, but acceleration and deceleration remain problematic. Starting from rest and establishing a warp bubble around your spacecraft requires energy configurations that might still demand exotic matter. The same applies to slowing down and collapsing the bubble safely at your destination. Some researchers are exploring whether rotating or oscillating field configurations might enable acceleration without exotic matter. Others investigate whether you could establish a warp bubble gradually, starting with a very weak effect and slowly intensifying it, distributing the energy requirements over time. These approaches remain speculative, requiring further theoretical and computational work to determine feasibility. Another open question involves warp bubble interactions. What happens if two warp bubbles encounter each other? Do they merge, bounce off, or mutually destabilize? If we eventually have multiple warp-capable spacecraft, understanding how they interact becomes essential for safe navigation. This is analogous to how ships must follow maritime rules to avoid collisions, but the physics is far more complex. The gravitational wave signature of a warp drive is another interesting question. General relativity predicts that accelerating masses produce gravitational waves, ripples in spacetime that propagate at light speed. A warp drive manipulates spacetime dramatically, so it should generate distinctive gravitational wave patterns. Future gravitational wave observatories might be able to detect warp-capable spacecraft across interstellar distances, providing a way to track their movements, or even detect alien civilizations using similar technology. This raises an intriguing possibility. Perhaps advanced civilizations already use warp drives or similar technologies, and we simply haven't recognized the signatures. Gravitational wave astronomy is still in its infancy, having made the first detections less than a decade ago. As our instruments improve and we accumulate more data, we might discover patterns that don't match natural astrophysical sources. These could be artifacts of technology, perhaps including propulsion systems. The hypothesis that we might detect alien civilizations through their technological signatures rather than deliberate communication attempts has gained traction recently. Techno-signatures could include atmospheric pollution on exoplanets, large-scale engineering projects like Dyson spheres, or, as we're discussing now, gravitational waves from advanced propulsion systems. This broadens the search for extraterrestrial intelligence beyond traditional radio Ceti. Searching for techno-signatures requires knowing what to look for, which is challenging when we're only familiar with one technological civilization, ourselves. We project our assumptions onto hypothetical aliens, imagining they'd use radio communications, build megastructures, or manipulate space-time. But truly advanced civilizations might employ technologies we can't conceive, making them invisible to our searches. This is sometimes called the cosmic haystack problem. We're searching for a needle while uncertain what needles look like or even if needles exist. Despite this uncertainty, searching remains worthwhile. The potential payoff, confirming we're not alone, learning from civilizations more advanced than ours, understanding our place in the cosmic story, justifies significant effort. The discovery would rank among humanity's most profound achievements, answering questions that have haunted us since we first gazed at stars and wondered. Warp drives connect to these grand questions in multiple ways. They represent our attempt to transcend limitations imposed by physics and distance. They embody hope that the universe's wonders are accessible, not forever beyond reach. They demonstrate human ingenuity, our capacity to take ideas from fiction, subject them to rigorous scientific analysis, and discover that they might actually work. And they provide a framework for thinking about what advanced civilizations could achieve and how we might detect them. As we approach the conclusion of this exploration, it's worth reflecting on how far we've come. We started with Miguel Alcubierre's paper in 1994, which showed that general relativity permits faster-than-light travel through space-time manipulation. We discussed how his design required exotic matter with negative energy density, a seemingly insurmountable obstacle that relegated warp drives to science fiction for decades. Then came the 2024 breakthrough by Alexei Bobrik, Gianni Martir, and their collaborators. By redesigning the warp bubble geometry to use gradual transitions rather than sharp discontinuities, they eliminated the exotic matter requirement. Their constant velocity warp drive works with only positive energy, transforming warp technology from physically impossible to merely extraordinarily difficult. This shift from never to maybe someday represents a fundamental change in how we should think about interstellar travel. We explored the immense challenges that remain, energy requirements that dwarf anything currently achievable, materials that must withstand extreme conditions, navigation systems for traversing causally disconnected space-time regions, and numerous other engineering obstacles. We discussed how these challenges, while formidable, don't violate known physics. They're problems of capability rather than fundamental impossibility, suggesting that sufficiently advanced technology might overcome them. We considered the broader context, humanity's growing catalogue of potentially habitable exoplanets, our search for extraterrestrial intelligence, the Fermi paradox, and what interstellar travel capability would mean for our civilization's long-term future. We examined how warp drive research connects to fundamental questions in physics, from quantum gravity to the nature of dark energy, and how pursuing such ambitious goals drives innovation across multiple fields. We also acknowledged uncertainties and unknowns. Quantum effects might destabilize warp bubbles in ways general relativity doesn't predict. The energy requirements might prove impossible to meet even with centuries of technological advancement. Acceleration and deceleration remain problematic. Countless engineering challenges await discovery. We might ultimately find that warp drives, while theoretically permissible, are practically unachievable. But the possibility exists. For the first time in human history, we have mathematically rigorous, peer-reviewed research demonstrating that faster-than-light travel doesn't violate the laws of physics as we understand them. This knowledge changes something fundamental about our relationship with the cosmos. The stars are no longer unreachable in principle, only in practice. And practices can change. Technologies advance. What's impossible for one generation becomes routine for another. Consider the progression. A century ago, powered flight was a recent novelty. 70 years ago, we entered space for the first time. 55 years ago, we walked on the moon. Today, we're landing reusable rockets, planning permanent lunar bases, and seriously discussing Mars colonization. In another century, perhaps we'll have fusion-powered spacecraft exploring the outer solar system. In 2 centuries, maybe the first warp bubble experiments will succeed in laboratories. In 3 or 4 centuries, the first interstellar missions might depart. This timeline is speculative, but the trajectory is plausible. Each generation builds on its predecessor's achievements, gradually expanding the envelope of possibility. What seemed like magic becomes engineering, and what seemed impossible becomes merely challenging. Warp drives fit into this pattern of incremental progress toward seemingly unreachable goals. For those of us alive today, warp drives will likely remain theoretical. We probably won't live to see operational spacecraft manipulating space-time for propulsion, but we're witnesses to the moment when serious physics established that it could work in principle. We're the generation that learned the universe might be more accessible than we thought, that the cosmic ocean might be navigable after all. That's a profound realization, one that should inspire wonder and determination. The practical implications for our daily lives are minimal. Warp drive research won't cure diseases, feed the hungry, or solve climate change. But it represents something equally important: vision. It demonstrates that humanity can think beyond immediate concerns to consider what we might become over centuries and millennia. It shows that we value knowledge and exploration for their own sake, not just for immediate utility. And it provides a North Star, a long-term goal that can inspire and guide us through nearer-term challenges. Education systems worldwide could benefit from incorporating these ideas. Students learning physics often ask, "When will I ever use this?" Warp drives provide a compelling answer. You might not use this directly, but understanding general relativity, energy conservation, and advanced mathematics opens doors to participating in humanity's grandest projects. The people who eventually build warp drives will need the knowledge you're learning now. That narrative is more inspiring than teaching formulas divorced from context. Science communication, the effort to make cutting-edge research accessible to general audiences, plays a vital role here. Most people lack the mathematical background to read peer-reviewed physics papers, but they can grasp the essential ideas if explained clearly. Videos, articles, podcasts, and educational content that translate technical concepts into everyday language democratize knowledge and help society make informed decisions about research priorities and funding. This is why platforms like this exist, to bridge the gap between specialists and the curious public. Complex topics like general relativity, exotic propulsion, and cosmology shouldn't be locked away in academic journals. They belong to everyone, part of our shared human heritage and future. Understanding that warp drives might actually be possible, what challenges they face, and what achieving them would mean, these insights should be widely accessible. As we conclude, let's acknowledge the profound uncertainty inherent in long-term predictions. History is full of confident forecasts that proved wildly wrong. In 1900, predictions for the year 2000 imagined flying cars and undersea cities, but missed computers and the internet entirely. Futurists in the 1950s envisioned nuclear-powered everything, but didn't foresee smartphones or social media. Our predictions about the 22nd or 23rd century will likely be similarly flawed. Warp drives might develop faster than expected if breakthrough discoveries enable shortcuts we can't currently imagine. Or they might prove impossible despite theoretical permissibility, defeated by engineering challenges that resist centuries of effort. Or, most likely, they'll fall somewhere between these extremes, eventually achieved but taking longer and following a more circuitous path than we anticipate. What we can say with confidence is that the research matters. Every paper that refines warp drive theory, every experiment that tests space-time manipulation at small scales, every technological advancement that reduces energy requirements or improves materials, these contributions move us incrementally closer to capabilities that currently seem magical. Whether that journey takes centuries or millennia, whether it succeeds or ultimately fails, the attempt itself ennobles humanity. We are a species that dreams of stars. We've always been explorers pushing beyond familiar horizons to discover what lies beyond. That impulse drove our ancestors out of Africa to populate the globe. It sent Polynesian navigators across vast oceans in outrigger canoes. It motivated European explorers to circumnavigate Earth. It propelled us to the moon and sent our robots to every planet in the solar system. Now it drives us to contemplate bending space-time itself to reach other stars. This isn't hubris or foolishness. It's vision, the uniquely human capacity to imagine futures that don't yet exist and work to bring them into being. Warp drives represent the ultimate expression of that vision, a technology that would let us transcend our cosmic confinement and become true citizens of the galaxy. Whether we achieve it in 3 centuries or 30, whether we succeed or find it forever beyond our grasp, the pursuit itself matters. So where does this leave us as we finish this journey through warp drive physics? With cautious optimism, I think. The 2024 research established that warp drives don't violate known physics when designed correctly. That's genuinely significant, but enormous challenges remain, and we should be honest about how difficult and uncertain the path forward appears. If you're a student considering a career in physics or engineering, know that fields like this need talented, dedicated people. The researchers who might eventually build warp drives are probably in school right now, learning the mathematics and physics that will form their foundation. You could be one of them. Even if warp drives never materialize, the skills you'd develop, advanced mathematics, computational modeling, experimental design, critical thinking, apply to countless other pursuits. If you're simply curious about the universe and our place in it, I hope this deep dive has enriched your understanding. The cosmos is stranger and more wonderful than everyday experience suggests. General relativity reveals that space and time are flexible, dynamic, and manipulable. Quantum mechanics shows that reality at its smallest scales is probabilistic and deeply weird. Astronomy demonstrates that we inhabit a universe containing hundreds of billions of galaxies, each with hundreds of billions of stars, many hosting planets, some potentially harboring life. Against this cosmic backdrop, warp drives represent both humility and ambition. Humility because the distances and energies involved remind us how small and limited we currently are. Ambition because we refuse to accept those limitations as permanent, choosing instead to imagine and work toward transcending them. That balance, acknowledging present constraints while striving to overcome them, characterizes humanity at our best. The story of warp drives is still being written. The 2024 breakthrough represents a chapter, not the conclusion. Future chapters will be written by researchers building on this work, exploring variations, solving problems, and gradually transforming theoretical possibility into engineering reality. Some of those researchers might be reading or watching this right now, inspired to pursue careers that contribute to humanity's interstellar future. To them, and to everyone who dreams of stars, I say, keep learning, keep questioning, keep pushing boundaries. The universe is vast and full of wonders waiting to be discovered. The technologies that will let us explore it directly don't exist yet, but they might someday, and every contribution moves us closer. Whether you work on warp drive specifically or any of the countless related fields, energy generation, materials science, gravitational physics, spacecraft engineering, you're part of the effort to expand human capability and understanding. The journey to the stars begins with a single step, or in this case, a single equation. Alcubierre took that step in 1994. Bobrick, Martyr, and colleagues took another crucial step in 2024. Many more steps remain, more than we can currently count, but each one matters. Each one brings closer the day when humans travel between stars, not in our imaginations or in fiction, but in reality, experiencing firsthand the wonders we've only glimpsed from afar. That future, if we achieve it, will transform everything. It will be humanity's greatest adventure, our most significant achievement, our graduation from a planetary species to a cosmic one. And it begins with research happening right now, physicists solving equations, engineers testing materials, visionaries communicating possibilities to inspire the next generation. Thank you for joining me on this exploration of warp drive physics, from theoretical foundations through technological challenges to philosophical implications. The universe awaits. Let's continue working toward the day when we can finally reach it. If you made this far, I am sure you will love this other video at the left side of the screen. Scientists revealed how far humans can travel through space. This comprehensive deep dive discover the ultimate boundaries of human space exploration, from the Moon and Mars to the edge of the observable universe and beyond. See you there.